Welcome! In this video, we'll dive into the problem count number of nice subarrays. This is an exciting challenge that combines array manipulation with counting techniques to find subarrays that meet specific criteria. Let's explore the problem and break it down step by step. In this problem, we need to count the number of nice subarrays in a given integer array nums with an integer k. A nice subarray is defined as a contiguous subarray that contains exactly k odd numbers. The input consists of an integer array nums where the size can range from 1 to 50,000, and each element is between 1 and 100,000. Additionally, the integer k will fall between 1 and the length of the array. The output should be a single integer, which represents the total number of such nice subarrays. Let's look at an example to clarify what this means. Suppose the input array is 1, 1, 2, 1, 1, and k is 3. The task is to find subarrays that contain exactly 3 odd numbers. In this case, 2 subarrays meet the criteria 1, 1, 2, 1, which spans indices 0 to 3, and 1, 2, 1, 1, which spans indices 1 to 4. Since there are 2 such subarrays, the output is 2. On the other hand, if the input array is 2, 4, 6, and k is 1, there are no odd numbers in the array, so it's impossible to form a subarray with exactly one odd number. Therefore, the output in this case is 0. Now consider another example where the input array is 2, 4, 6, 1, 1, 1, and k is 2. Here, we are looking for subarrays that contain exactly 2 odd numbers. The valid subarrays are 1, 1, from index 3 to 4, 1, 1, from index 4 to 5, and 1, 1, from index 3 to 5. This gives a total of 3 subarrays that satisfy the condition, so the output is 3. These examples illustrate how the problem requires identifying specific contiguous subarrays based on the count of odd numbers they contain. There are a few constraints and edge cases to keep in mind for this problem. First, the size of the array can go up to 50,000, so an efficient solution is necessary to avoid time limit issues. A naive approach with n squared complexity will not work for larger inputs, so we need to consider optimized techniques like the sliding window or prefix sum approach. Additionally, if the array contains no odd numbers, the result will always be 0 for any value of k. Similarly, if k is greater than the total number of odd numbers in the array, the result is also 0. On the other hand, if the array contains only odd numbers, the problem reduces to finding contiguous subarrays of length k. These considerations are critical for designing an efficient and robust solution. To tackle the problem of counting subarrays with exactly k odd numbers, we explored a few potential approaches. The most straightforward method is the brute force approach. Here, the idea is simple: iterate over all possible subarrays of the given array nums. For each subarray, count how many odd numbers it contains. If the count matches k, we increment our result. To implement this, we would use 2 nested loops to generate all subarrays, and for each subarray, an additional loop to calculate the number of odd numbers. However, while this approach is easy to grasp and implement, it is computationally expensive. Generating subarrays has a time complexity of n superscript 2, and counting odd numbers for each subarray adds another n, resulting in an overall complexity of n superscript 3. This makes the brute force approach impractical for large input sizes, as it becomes prohibitively slow. Let's look at more efficient alternatives. Now, a more efficient strategy is the sliding window approach with 2 pointers. The key insight here is that instead of iterating over all subarrays, we can maintain a dynamic window of elements and adjust it as needed while keeping track of the number of odd numbers. Using 2 pointers, we define the boundaries of this window. The right pointer expands the window to include new elements, and each time the count of odd numbers exceeds k, the left pointer is moved to shrink the window until the count is back to k. During this process, we keep track of how many subarrays satisfy the condition. The advantage of this method is its efficiency: it processes each element at most twice, resulting in an n time complexity. However, implementing this approach can be tricky, as we must carefully manage the movement of the pointers and ensure all valid subarrays are counted. While efficient, this method can be error-prone, especially in handling edge cases. An even more optimized solution leverages the prefix sum technique combined with a hash map. The core idea is to transform the problem into one involving prefix sums. By keeping a running count of the cumulative number of odd numbers encountered up to each index, we can reduce the problem to finding subarrays where the difference between two prefix sums is exactly k. To implement this, we maintain a hash map that records the frequency of each prefix sum. For every prefix sum, we check if there exists a prior prefix sum whose difference with the current one equals k. If such a prior prefix sum exists, it indicates that the subarray between their indices contains exactly k odd numbers, and the frequency of that prior sum tells us how many such subarrays exist. This approach processes the array in linear time, O(n), and requires O(n) additional space for the hash map. It is highly efficient and eliminates the complexity of managing a sliding window, though it does require extra memory. This trade-off makes it an excellent choice for most scenarios. Ultimately, we selected the optimized prefix sum approach as the best strategy. Its efficiency, clarity, and scalability made it the ideal choice for this problem. By reframing the problem as a prefix sum difference query, the solution becomes both intuitive and straightforward to implement. The trade-off in memory usage due to the hash map is minimal compared to the benefits of O(n) time complexity. While the sliding window approach is also efficient, it introduces unnecessary complexity with the dynamic adjustment of two pointers and is more prone to errors in corner cases. The brute force method, on the other hand, was dismissed early due to its prohibitive time complexity. In summary, the prefix sum solution strikes the right balance between simplicity and performance, making it the most suitable approach for counting nice subarrays with exactly k odd numbers. The problem we are solving is to count the number of nice subarrays in a given array of integers. A subarray is defined as nice if it contains exactly k odd numbers. For example, if we have the array nums equals 1, 1, 2, 1, 2, and k equals 2, the subarrays 1, 1, 1, 1, 2, and 1, 2, 1 each contain exactly two odd numbers, making them nice. To solve this, we could start with a brute force approach. This would involve iterating over all possible subarrays, counting the odd numbers in each subarray, and checking if the count equals k. If it does, we increment the result. However, this method is inefficient, with a time complexity of O(n) cubed, due to the nested loops required to generate subarrays and count their odd numbers. To optimize, we can use a combination of prefix sums and a sliding window technique to find these subarrays more efficiently. To develop an efficient algorithm, we first pre-process the array. This involves converting the original array nums into a binary array called is_odd, where each element is either 1 if the corresponding number in nums is odd, or 0 if it is even. This simplifies the problem to counting the sum of ones in subarrays. Next, we use a hash map, prefix_count, to store the frequency of prefix sums encountered during our traversal. This hash map helps us track how many times a particular cumulative sum has occurred, which is critical for determining subarrays with exactly k odd numbers. We initialize prefix_count 0 to 1 to handle cases where a subarray starts at the beginning of the array. As we iterate through the array, we maintain a running sum, current_sum, of the elements in is_odd. At each step, we calculate current_sum k. If this value exists in prefix_count, it means there are subarrays ending at the current index that contain exactly k odd numbers. We add the count stored in prefix_count, current_sum k, to our result. Finally, we update prefix_count with the current sum to include it in our tracking. This approach ensures that we count all nice subarrays efficiently. The key insight for solving this problem lies in the conversion of odd and even numbers into binary values. By reducing the array to ones and zeros, we simplify the task to a prefix sum calculation. The difference current_sum k allows us to quickly determine if there exists a subarray ending at the current index with exactly k odd numbers. The use of a hash map, prefix_count, is critical for efficiency. It allows us to track how many times each prefix sum has occurred and retrieve this information in constant time, which drastically reduces the complexity compared to the brute force method. From a data structure's perspective, the hash map is essential for storing prefix sums and their frequencies, while the binary array is_odd transforms the problem into one focused solely on counting. This results in a time complexity of O(n), since we only make a single pass through the array, and each hash map operation is O(1). The space complexity is also O(n), as the hash map can store at most n+1 unique prefix sums. Overall, this optimization makes the solution both elegant and efficient, suitable for large input sizes. Let's walk through an example to see the algorithm in action. Suppose we have nums equals 1, 1, 2, 1, 2, and k equals 2. First, we convert nums into the binary array as _odd, which becomes 1, 1, 0, 1, 0. We then initialize our hash map, prefix _count, with 0, 1, and set current _sum and result to 0. As we iterate through is _odd, we compute the running sum and update the hash map. At index 0, current _sum is 1, and prefix _count becomes 0, 1, 1, 1. At index 1, current _sum increases to 2, and we update prefix _count to 0, 1, 1, 1, 2, 1. At index 2, current _sum remains 2. Here, we find that prefix _count, 2 to 2, equals 1, so we add 1 to our result. The hash map updates to 0, 1, 1, 1, 2, 2. At index 3, current _sum becomes 3. Again, prefix _count, 3 to 2, equals 1, so we add another 1 to the result, and the hash map updates to 0, 1, 1, 1, 2, 2, 3, 1. At index 4, current _sum remains 3, and prefix _count, 3 to 2, equals 1, so we add 1 more to the result. The final hash map is 0, 1, 1, 1, 2, 2, 3, 2. The total result is 3, which matches the expected output. This step-by-step process demonstrates the efficiency and accuracy of the optimized algorithm. The solution uses a sliding window approach to efficiently count the number of subarrays containing exactly k odd numbers. The key insight is to count subarrays with at most k odd numbers and at most k1 odd numbers, then subtract the latter from the former to get the count for exactly k. First, that at most k helper function is defined. It initializes count to store the total number of valid subarrays, left as the left boundary of the sliding window, and odd _count to track the number of odd numbers in the current subarray. We iterate through the array using the right pointer. If the current number, nums, right, is odd, we increment odd _count. When odd _count exceeds k, we shrink the window by moving left to the right until odd _count is within the limit. For each right position, the number of valid subarrays is determined by the window size, right left plus 1, and added to count. Finally, the main function calculates the difference between the results of at most k, k, and at most k, k1, to find subarrays with exactly k odd numbers. This approach is efficient, with a time complexity of O, n, as each element is processed at most twice, once by right and once by left. The space complexity is O, 1, as no additional data structures are used. Here, we begin with the definition of the number of subarrays method, which is the main function designed to calculate the number of nice subarrays in the given array nums with exactly k odd numbers. To achieve this, we utilize a helper method called at most k and compute the difference between the results of at most k, nums, k, and at most k, nums, k1. This approach works because the number of subarrays with exactly k odd numbers can be determined by subtracting the count of subarrays with at most k1 odd numbers from those with at most k odd numbers. Next, we define the at most k function. Inside this function, we initialize three variables: count, which will track the total number of valid subarrays, left, which serves as the starting index of our sliding window, and odd count, which tracks the number of odd numbers in the current window. We then use a for loop to iterate through the array, with right representing the ending index of the sliding window. For each element, if the current number is odd, we increment odd count, as we now have one more odd number in our window. After that, we ensure that the window remains valid by shrinking it whenever odd count exceeds k. This is done by incrementing the left pointer and reducing odd count if the element at the left index is odd. Once we have adjusted the window so that it contains at most k odd numbers, we calculate the number of valid subarrays that end at the current index right. This is done by adding the length of the current window, which is given by right left plus 1, to the count variable. This step ensures we account for all subarrays within the valid range. Finally, when the loop completes, we return the total count, representing the number of subarrays with at most k odd numbers. By subtracting the results of at most k, nums, k1, from at most k, nums, k, in the main method, we effectively isolate and return the count of subarrays with exactly k odd numbers. This efficient sliding window approach ensures that we process the array in linear time, making it highly scalable for large inputs. To solve this problem, we need to count subarrays with exactly 3 odd numbers. The key observation here is that we can calculate this by finding the difference between subarrays with at most 3 odd numbers and subarrays with at most 2 odd numbers. Specifically, the formula is subarrays with exactly k odd numbers equals at most k minus at most k1. Now, we begin by calculating at most k3 for the array 1, 1, 2, 1, 1. We initialize 3 variables, count, left, and odd_count, all set to 0. As we iterate through the array, we adjust these values based on whether the current element is odd or even. In the first iteration, nums 0 is 1, which is odd, so we increment odd_count to 1. Since odd_count is less than or equal to 3, we add 1 subarray, which is the current window, 1. This brings count to 1. In the second iteration, nums 1 is also odd, increasing odd_count to 2. We now add 2 subarrays, 1, 1, and 1, bringing count to 3. Continuing with at most k3, in the third iteration, nums 2 is 2, an even number, so odd_count remains unchanged. Here, we include all subarrays in the current window, which are 1, 1, 2, 1, 2, and 2. Adding these 3 subarrays brings count to 6. In the fourth iteration, nums 3 is 1, an odd number, so odd_count increases to 3. Again, odd_count is still within the limit, so we add 4 subarrays, 1, 1, 2, 1, 1, 2, 1, 2, 1, and 1. This brings count to 10. In the fifth iteration, nums 4 is 1, another odd number, increasing odd_count to 4, which exceeds the limit. To fix this, we shrink the window from the left by incrementing left until odd_count is back within the limit. Removing nums 0, which is odd, reduces odd_count to 3 and moves left to index 1. We then add 4 subarrays, 1, 2, 1, 1, 2, 1, 1, 1, 1, and 1. This results in a final count of 14 for at most k3. Next, we calculate at most k2 by repeating the same sliding window process but limiting odd_count to 2. Following this approach, we find that at most k2 equals 8. Using the formula, we can now calculate the number of subarrays with exactly 3 odd numbers as at most k3 minus at most k2, which is 14 minus 8, giving us 6. Moving on to another example, we consider nums equals 2, 4, 6, and k equals 1. Here, we start by calculating at most k1. Initialize count, left, and odd_count to 0. In the first iteration, nums 0 is 2, an even number, so odd_count remains 0. We add 1 subarray, 2, bringing count to 1. In the second iteration of at most k1, nums 1 is 4, also an even number, so odd_count remains 0. We add 2 subarrays, 2, 4, and 4, bringing count to 3. In the third iteration, nums 2 is 6, another even number, so odd_count still remains 0. We include 3 subarrays, 2, 4, 6, 4, 6, and 6, bringing count to 6. Therefore, at most k1 equals 6. Now, for at most k0, since k is 0, any subarray containing an odd number is invalid. Hence, at most k0 equals 0. Using the formula, the number of subarrays with exactly one odd number is at most k1 minus at most k0, which is 6 minus 0, resulting in 0. For the final example, nums equals 1, 2, 1, 2, 1, and k equals 2, we first calculate at most k2. Initialize count, left, and odd_count to 0. In the first iteration, nums 0 is 1, an odd number, so odd_count increases to 1. We add 1 subarray, 1, bringing count to 1. In the second iteration, nums 1 is 2, an even number, so odd_count remains 1. We add 2 subarrays, 1, 2, and 2, bringing count to 3. In the third iteration, nums 2 is 1, an odd number, so odd_count increases to 2. We add 3 subarrays, 1, 2, 1, 2, 1, and 1, bringing count to 6. In the fourth iteration of at most k2, nums 3 is 2, an even number, so odd underscore count remains 2. We include 4 subarrays, 1, 2, 1, 2, 2, 1, 2, 1, 2, and 2, bringing count to 10. In the fifth iteration, nums, 4, is 1, an odd number, increasing odd underscore count to 3, which exceeds the limit. To adjust, we shrink the window by removing nums, 0, reducing odd underscore count to 2 and moving left to index 1. We then add 4 subarrays, 2, 1, 2, 1, 1, 2, 1, 2, 1, and 1. This results in a final count of 14 for at most k, 2. For at most k, 1, repeating the process gives a result of 9. Using the formula, the number of subarrays with exactly 2 odd numbers is at most k, 2, minus at most k, 1, which equals 14 minus 9, giving us 5. The time complexity of our solution revolves around the sliding window technique. To analyze this, let's start with the inner loop inside the at most k function. Here, the while loop works to shrink the window whenever the count of odd numbers exceeds k. The left pointer, which controls the shrinking, moves forward one step at a time and advances at most once per element in the array nums. This means that over the course of the entire algorithm, the left pointer executes no more than n operations, where n is the length of the input array. Now, looking at the outer loop, the for loop expands the window by iterating over each element in nums. Since every element is processed exactly once during this expansion, the total operations for the outer loop are also proportional to n. Combining the two loops, each element in the array is processed at most twice, once when expanding and once when shrinking, resulting in a time complexity of O, n, for a single call to at most k. To determine the overall time complexity of the solution, note that it involves 2 calls to the at most k function, one to calculate the result 4k and another for k1. Since each call to at most k has a time complexity of O, n, the total time complexity becomes O, n, plus O, n, which simplifies to O, n. As for the space complexity, the algorithm uses only a constant amount of additional space. Temporary variables such as count, left, odd underscore count, and loop indices are created, but these do not depend on the size of the input array. Furthermore, no auxiliary data structures like arrays or hash maps are used, and the algorithm operates directly on the input array without making any copies. Therefore, the space complexity is O1, as the amount of memory used remains constant regardless of the input size. To better appreciate the efficiency of the sliding window approach, let's compare it to a brute force solution. In a naive approach, you would iterate over all possible subarrays of the input array nums. For an array of length n, there are approximately n asterisk, n plus 1, / 2 subarrays, and for each subarray, you would need to count the number of odd elements, which could take up to O, n, operations in the worst case. This leads to a time complexity of O, n cubed, which quickly becomes infeasible for large inputs. In contrast, the optimized sliding window approach avoids redundant computations by maintaining a dynamic window and leveraging the properties of contiguous subarrays. As a result, the time complexity is reduced to O, n, making it dramatically more efficient and suitable for larger datasets. Now, let's analyze the algorithm in different scenarios. In the best case, such as when all elements in the array are even or when k is very small, the algorithm still traverses the entire array, giving it a time complexity of O, n. For the average case, where the array contains a mix of odd and even numbers, each element is processed at most twice, once during expansion and once during shrinking, so the performance remains linear. Even in the worst case, where all elements are odd, the sliding window expands and shrinks fully, but the total number of operations is still bounded by O, n. To understand why this is the case, note that the sliding window ensures both the left and right pointers traverse the array at most once. Hence, the number of operations is directly proportional to the size of the input n. Moreover, since the algorithm does not use additional memory that scales with the input size, the space complexity remains O1. When solving this problem, there are a few common mistakes to avoid. One of the most frequent errors is incorrect handling of odd numbers. For instance, if you fail to reset the count of odd numbers when moving to a new subarray, you might miscount and end up with invalid boundaries, which will lead to incorrect results. Always ensure the count is updated correctly with every iteration. Another common issue is relying on a brute force approach without optimization. Using nested loops to calculate all possible subarrays and count the odd numbers in each might seem straightforward, but it leads to a time complexity of O, n cubed. For larger arrays, this is highly inefficient and can result in time limit exceeded errors. Finally, misusing prefix sums is another pitfall. For example, forgetting to account for edge cases, such as when the array has fewer odd numbers than k or no odd numbers at all, can lead to off-by-one errors or incorrect results when calculating valid subarrays. These are critical aspects to watch out for as you refine your solution. Another area where mistakes happen is handling boundary conditions. If the start and end of the array aren't managed properly, especially when working with small arrays or when k exceeds the total number of odd numbers, you may encounter issues like index out-of-bound errors or fail to identify valid subarrays. It's essential to carefully manage these edge cases. Similarly, improper use of hash maps or the sliding window technique can cause problems. For instance, if you forget to reset the hash map or the sliding window when conditions change, you might end up counting invalid subarrays or completely missing valid ones. These techniques are powerful, but they require careful implementation to ensure correctness. Understanding the insights behind this problem can make a big difference, especially in an interview setting. One key insight is recognizing the pattern that this problem boils down to finding subarrays with a specific property, exactly k odd numbers. Once you identify this, you can apply optimized techniques like sliding window or prefix sums. An optimal approach involves using prefix sums with a hash map to efficiently count the number of subarrays with exactly k odd numbers, which reduces the time complexity to O(n). It's also important to handle edge cases thoroughly. For example, consider arrays with no odd numbers, arrays smaller than k, or scenarios where k is 0. Discussing these edge cases during an interview demonstrates your attention to detail. Additionally, there are trade-offs to consider. While brute force methods are easier to implement, they're inefficient. Sliding windows are faster but require precise boundary management, and prefix sums with hash maps are the most efficient but involve more advanced debugging skills. If you're preparing for interviews, it can also be helpful to study related problems like LeetCode 930, 560, and 209, which involve similar concepts such as subarray sums and sliding window techniques. There are a few alternative approaches to solving this problem, each with its own advantages and trade-offs. The sliding window method works by maintaining a window that contains at most k odd numbers. You dynamically adjust the window size as you iterate through the array, counting valid subarrays along the way. While this approach is efficient and avoids the additional space complexity of hash maps, it can be slightly harder to implement, as it requires carefully managing the window boundaries. Another option is using prefix sums combined with a hash map. Here, you track the cumulative count of odd numbers at each index and store these counts in a hash map for efficient retrieval. This approach is the most efficient, with a time complexity of O(n), but it does require a solid understanding of hash map operations and careful debugging for corner cases. Finally, there's the brute force approach, where you iterate through all possible subarrays and count the odd numbers in each one. While this method is simple to implement, it's highly inefficient for large inputs due to its O(n)³ complexity. Choosing the right approach depends on the problem constraints and your familiarity with these techniques. Great job! We've successfully solved the problem by applying a combination of prefix sums and sliding window techniques. Remember, understanding the trade-offs in time and space complexity is key to mastering algorithmic thinking. Thanks for watching, and be sure to subscribe for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!